Okay, so I am back with the solutions to the homework problems for page 271 to 272, numbers 3, 16, and 17. I will pause for a few seconds to give you a chance to turn off the video so you can check your answers, and then I'll show you the next one. Here is 16b. C, 16D, and then 17A, 17B, 17C, and 17D. Now what I'll do is go through each of these and show you how to do each problem in case you have any questions. So starting with number 3, I'm just going to show you my answer again for number 3 here. It says, after pumping air into a bicycle tire, you notice that the nozzle on the pump is quite hot. Why? What gas law applies to this situation? Compressed air gets hotter. Remember, we said that as we decrease the volume, as we increase the pressure, the temperature gets higher, okay? As we increase the pressure, the temperature gets higher. As we squeeze those gas particles together, there's just going to be more friction and things in there that increase that temperature, okay? And this is Gay-Lussac's law. Okay, so going to 16. So this is 16A. The problem says, a sample of nitrogen gas occupies 130 milliliters at 20 degrees Celsius. What volume will the gas occupy at 45 degrees Celsius if the pressure remains constant? So these are all Charles' law. So this is volume over temperature. So we find our V1 and our T1. Our initial volume is 130 milliliters. Our initial temperature is 20 degrees Celsius, but we have to convert that to Kelvin. So it's 293 Kelvin. We are looking for the final volume, and the final temperature, they say, is 45 degrees Celsius. Convert that to Kelvin, and we have 318 Kelvin. So we will plug those numbers into our equation. V1 over T1 equals V2 over T2. Plugging the numbers in, I have 130 milliliters over 293K equals V2 over 318K. I'm going to multiply both sides by 318 to get to V2 by itself. So 130 milliliters times 318 K over 293 K is V2. Okay, so V2 equals, when I multiply these two numbers together, I get 41,340 milliliters over 293. And when I do the division, I end up with 140 milliliters, which we expect if we increase the temperature, we will increase the volume. So that checks out. For B, the question is, a particular tank of oxygen contains 785 liters at 21 degrees Celsius. If the pressure remains constant, what volume will the gas occupy if the temperature is changed to 28 degrees Celsius? Now, this law is the reason also, well, actually, I'm thinking Gay-Lussac's law is the reason, because of the increase in pressure, that they tell you to store aerosol cans at certain temperatures, because if you increase the temperature, it's going to increase the pressure, and that can cause the can to burst. So these laws are very applicable to real life. Okay, so my initial volume is 785 liters. My initial temperature is 21 degrees Celsius. Convert that to Kelvin, and I get 294 Kelvin. I'm looking for my final volume, and my final temperature is 28 degrees Celsius. Convert to Kelvin, and I have 301 Kelvin. Whoops. Sorry, you didn't see that. There it is. Okay. So my equation V1 over T1 equals V2 over T2. Plug in my numbers. 785 liters over 294 Kelvin equals V2 over 301 Kelvin. Multiply both sides by 301 Kelvin. So I get 785 liters. Whoops. Nope. Don't want to cross out the whole thing, do I? Just the units. So V2 equals, multiplying the top numbers together, I get 236,285 liters over 294. Do the division, and I get 804 liters. My temperature went up, so I expect my volume to go up. Okay, for C. The question says, an experiment calls for 5.50 liters of sulfur dioxide at 0 degrees Celsius in 1 atmosphere. What would the volume of this gas be at 30 degrees Celsius if the pressure remains constant? So for C, my initial volume is 5.5 liters. My initial temperature is 0 degrees Celsius. Convert it to Kelvin, and I have 273 K. My final volume is what I'm looking for. My final temperature is 30 degrees Celsius. Convert that to Kelvin, and I have 303 K. Plug that into my equation. V1 over T1 equals V2 over T2. I plug in my numbers, 5.50 liters over 273 K equals V2 over 303 K. Multiply both sides by 303 K. So V2 equals, multiplying those top two numbers together, I get 1,666.5 liters. Divide by 273, which equals 6.10 liters. 3 sig figs carried through because of this number here, not 1. Okay, and then D. So D is, at 19 degrees Celsius, a chemical reaction produces 4.30 milliliters of oxygen gas. How much oxygen gas would be produced at 45 degrees Celsius if the pressure remains constant? So V1 is 4.30 milliliters. T1, 19 degrees Celsius. Convert that to Kelvin, and I get 292 Kelvin. V2 is what I'm looking for, and T2 is 45 degrees Celsius. Convert that to Kelvin, and I get 318 Kelvin. Plug it into my equation of V1 over T1 equals V2 over T2. And you guys didn't see any of that, did you? I've got to remember to move up my paper. Sorry, there it is. .30 milliliters. Plug in my numbers. Multiply both sides by 318 Kelvin to get V2 by itself. And V2 equals, multiplying 4.3 times 318, I get 1,367.4 milliliters over 292. Do the division, and that's 4.68 milliliters. And in this case, the temperature increases, we expect the volume to increase, because this is a direct relationship. Okay, for 17, these all have to do with Gay-Lussac's law. So 17A. A gas occupying half a liter at 1200 torr and 16.5 degrees Celsius undergoes a temperature change so that the pressure is now 300 torr. If the volume has remained constant, what is the new temperature? So here I'm working with pressure and temperature. And my initial pressure is 1200 torr. That decimal point is very important because that tells me I have 4 significant digits. So keep that. Temperature is 16.5 degrees Celsius. Convert that to Kelvin. And I get 289.5 Kelvin. My final pressure is 300 torr. Again, make sure you keep that decimal for 3 significant digits, and I want to know the new temperature. So my equation, P1 over T1 equals P2 over T2. Plug in my numbers, 1200 torr over 289.5 Kelvin is 300 torr over T2. Okay, in this case, I'm going to want to cross multiply. So T2 times 1200, don't drop that decimal point, remember, that's important, equals 289.5K times 300 torr. I want to now divide both sides by 1200 torr to get T2 by itself. So T2 equals 6,850K over 1200. When we do the division, it's 72.4K. So in this case, we expect that if we drop the pressure, we're going to drop the temperature, because the kinetic energy of, if we drop the temperature, the kinetic energy is decreasing. And so there is less pressure because they're going slower. They're moving more slowly. Okay, for B. A reaction requires 1.5 milliliters of ammonia if it occurs at 1.65 atmospheres and 23 degrees Celsius. If the temperature is changed to 30 degrees Celsius, what will the new pressure be if the volume remains constant? So again, P1 and T1. My P1 is 1.65 atmospheres. My T1, 23 degrees Celsius, convert that to Kelvin, and I get 296 Kelvin. My P2 is what I'm after, and my T2 is 30 degrees Celsius. Convert that to Kelvin, and I get 303 Kelvin. So P1 over T1 equals P2 over T2. Plug in the numbers, 1.65 atmospheres over 296 Kelvin equals P2 over 303 Kelvin. Here I can multiply both sides by 303. So P2 equals 499.95 atmospheres. I'm keeping as many significant digits as possible, divided by 296, and I'll round later. And I get 1.69 atmospheres, 3 significant digits because I have 3 up here. Okay, so 2 more problems to go. Here is 17C. And the problem says, at 1.25 milliliters, a 1.25 milliliter sample of a colorless, odorless gas had a pressure of 806 torr at 120 degrees Celsius. If the volume remained constant, what would the gas's pressure be if the temperature dropped to 100 degrees Celsius? Okay, so my P1 and my T1. P1 is 806 torr. T1, 120 degrees Celsius, convert that to Kelvin, and I get 393 Kelvin. P2, I'm looking for T2, 100 degrees Celsius, convert that to Kelvin, and I get 373 Kelvin. Now, the reason they're making us convert each time is because what do we measure with in the lab? We measure in degrees Celsius. And you would have to convert all of these numbers to Kelvin. I don't have Kelvin thermometers in my lab. I have Celsius thermometers in my lab. All right, so our equation, plug in my numbers, 806 torr over 393K equals P2 over 373K. Multiply both sides by 373K. So P2 equals 300,638 torr over 393, which when we do the division is 765 torr. And we would expect if we drop the temperature that the pressure would in fact drop. Okay, and finally D, and I'm actually going to remember to move it up ahead of time, yay, on the last problem. Okay, so D says, just making sure I'm on the right problem, yep. A 3.20 milliliter sample of hydrogen sulfide had a pressure of 970 torr at 55 degrees Celsius. At what temperature would the pressure drop to 900 torr? So, identify my initial pressure and temperature. I have 970 torr, temperature of 55 degrees Celsius, convert to Kelvin, I get 328 Kelvin. Remember, we do this because they haven't given us a problem with a negative number, but realistically, you could do these problems with negative numbers. I don't know why they haven't given us negative numbers for any of these. Because it would help you understand better why we need to use Kelvin. P2 is 900 torr, and we're looking for the final temperature. Okay, so our equation, one last time, P1 over T1 equals P2 over T2. We have 970 torr over 328K equals 900 torr over T2. Here we have to cross multiply. So T2 times 970 torr is 328K times 900 torr. Now we divide both sides by 970. T2 equals, multiplying those top numbers together, 295,200K divided by 970 equals 304 Kelvin. And we would expect if we have a pressure drop that we have a temperature drop. Okay, so that is all of the homework problems for this section. I'll be back next week with some more videos. And next week we're going to combine all of the gas laws together.